Let's look at how the structure of an acid in its molecule would affect the strength of that acid. Does the strength of the bond between the acid hydrogen and the rest of the molecule affect the strength of the acid? The answer is yes. Let's look at hydrogen compounds in general. If a bond is polar and the hydrogen in that bond is slightly positive, as in hydrochloric acid or water, the hydrogen is bonded to a nonmetal with a pretty high electronegativity. The compound then will act as a strong or weak acid. If the bond is polar and the hydrogen is slightly negative, this would be a hydride. When it's bonded to a metal like sodium or calcium, the compound acts as a strong or weak base. If the bond is nonpolar, as in methane, ethane, things like that, there is neither acid nor base properties. We've seen that in earlier videos. Now, if oxygen is involved in the compound, we can predict the acid or base properties. First, oxides of metals will form bases in water. This is a reality that's been known for well over 100 years. So if you put sodium oxide into water, you get sodium hydroxide. If you put magnesium oxide in water, typically hot water, it will make magnesium hydroxide. Oxides of nonmetals, however, will form acids in water. So sulfur dioxide in water makes sulfurous acid. Diphosphorus pentoxide in water makes phosphoric acid. And you may already be aware that sulfur trioxide in water gives you sulfuric acid. Now, when acids are structured so that an acidic atom H is in a hydroxide group that's bonded to another atom Y, the more electronegative Y is, the more acidic is the acid. Of course, that's because the Y is withdrawing electrons from any other bonds around it, pulling the electrons toward itself. And the acid then has less electron covalency to bond it to the nearby hydroxide oxygen. So, for instance, if you look at HOCl, chloride has a high, not quite as high as fluorine, but a high electronegativity. And so it's going to pull electrons toward itself. This has a Ka of 3 times 10 to the negative 8th. Whereas HOI, the iodine, has a lower electronegativity than the chlorine, and so it's going to pull electrons less, and that means that there is a stronger bond between the oxygen and the hydrogen here in this OH pairing of the HOI. That means, of course, that this has a higher acidity, the HOCl, than the HOI. The numbers show it, and the electronegativity of the Y atom, chlorine or iodine, will explain that difference. Now, as a function of the number of oxygens in a molecule, we know oxygen is highly electronegative. So the more oxygens are in an oxyacid, the smaller the pull on the hydrogen that is coming off as the Bronsted-Lowry acid. More oxygens means a stronger acid. So we have a very good series here in hypochlorous, chlorous, chloric, and perchloric acid, whereas you can see going from left to right, we have Ka's here. This is a very low Ka. This is kind of mid-range Ka. Chloric is a fairly strong acid, and perchloric is one of the big 6 strong acids. And what's the difference? Well, oxygen here, just 1 to withdraw electrons. Here, 1, 2 oxygens in this molecule to withdraw electrons. In chloric, 1, 2, 3 oxygens pulling on the electrons along with the chlorine, so the hydrogen is a lot easier to get off. And finally, in perchloric, you have 4 oxygens pulling on electrons, and this makes this such a strong acid that it is 100% dissociated when you put it into water. So the more oxygens you have in a molecule that is an acid, the stronger is the acid. So, draw the Lewis structures for these 8 compounds and choose the strongest acid in each pair. Turn off the video and check your answers when you come back. The boldened and yellow acids are the strongest acid in each pair of acids. Now, when you have a carboxylic acid, you get resonance. Carboxylic acids are the ones with functional group COOH, and here is the shape. You may have seen it before. Experiment shows that this carboxyl functional group has resonance characteristics. Remember, resonance means where is the double bond? It can be between 2 atoms or 2 other atoms. In a sense, it kind of like it can shift. Now let's look a little closer at that. If you look at the 2 ways to draw the, in this case, the acetate ion, you can see that you can put the double bond either here or here, and here you can see it put in the other way. Traditionally, we show that as a resonance hybrid, but what is really happening is that the carboxyl carbon, this carbon here, is sp2 hybridized. And what that means is it's got the pi bond between the carbon and the oxygens, because the oxygens as well are sp2 hybridized. What this does, when you can draw it either way, when you've got the sp2 hybridization spread across these molecules and you're not quite sure where the bond is, that gives a lower energy than if the bonds were fixed in position. And with the lower energy, of course, that means you have a higher acidity. The OH bond then between the whichever oxygen you're talking about and the hydrogen that would come off it for an acid, the hydrogen then is more loosely bound to the base. So, looking at this, and from what you've seen in this video, answer, which of the hydrogen atoms in this molecule would have the greatest acid character, would be the one easiest to get off? Number 1 over here on this OH, number 2 on this NH2, number 3 on this more alkyl hydrogen, and number 4 on this carboxyl. Turn the video off and then come back and check. Hydrogen number 4, since it's attached to the carboxyl base, has the most acid character.